Well, hello everybody, and this is AP Chem exam review, acid-base chemistry, and it's a flash review, meaning everything is done fast. So, starting off with definitions. Well, we have three types of definitions, right? We have Arrhenius, and we have Lowry-Bronsted, and we have Lewis, right? Now, Arrhenius are what? It's an acid is a substance which increases the H plus concentration when dissolved in water. A base is a substance which increases the hydroxide concentration when dissolved in water. Now, what is a Lowry base? A Lowry-Bronsted acid. This is a proton donor. And what is a proton? Well, it's H plus. And then a base is a proton acceptor. Cool. And then what is a Lewis definition? Well, then an acid is a substance capable of accepting an electron pair. So it's an electron pair acceptor in a compound and an electron pair donator in a compound is a Lewis base. And so a typical Lewis base is something like ammonia, because it has an unshared pair here that it can, when it forms a compound, it can donate that. It's not really donating, it's not transferring. And then a typical Lewis acid is something like boron trichloride and also metal cations. So your metal cations are also typical, especially D block. D block metal cations tend to act like Lewis acids. Good. Conjugates. Conjugates have to do with our second definition, our Lowry-Bronsted, right? And so if I have something like nitrous acid plus water, and what are we going to form? We're going to form hydronium plus nitrite. In every Lewis-Bronsted acid-base reaction, there is an acid and a base on one side and an acid and base on the other. And so how do we figure this out? My hydrogen is being transferred here. So this is my Lowry-Bronsted acid. This is my proton acceptor. This is my Lowry-Bronsted base. Now, for this acid, there is a conjugate base, meaning after the proton is transferred, what do you have? Well, that's my conjugate base of HNO2. And for every Lowry-Bronsted base, there is a conjugate acid, which is the base after it has accepted the proton. There we go. And so that's all we need to know about conjugates. Now, having spoken about that, we're going to want to talk about strength kind of things. And we have something called strong and weak acids. Now, this is a case where we're saying strong and, weak acids. And what do I mean by that? A strong acid, by definition, is a strong electrolyte. And what are my strong electrolytes? Well, they are HCl, HBr, HI, yikes, HNO3, HClO4, that's nice, pretty, HClO3, and the first hydrogen coming off of sulfuric acid. Those are my strong acids. Everything else we were assuming is a weak acid. Good. Now, a weak acid is what? It is a weak electrolyte by definition. So when I'm saying, hey, is it a weak acid or a strong acid, that all depends on if it's a weak or strong electrolyte. And electrolytes are what? They form, when they dissolved, there is an equilibrium between the molecule and the ions, right? So all of these are present in a weak acid. Good. But we want strong and weak have specific definitions. Now, comparing that to stronger and weaker, well, stronger and weaker depends on the K. In this, if we're talking about Ka, the larger the K, if something has a larger Ka, so we'll say that this is Ka for, how about acetic acid? So Ka for acetic acid is 1.8 times 10 to the minus 1.8 times 10 to the minus fifth, and versus the Ka for cyanic acid, 3.5 times 10 to the minus fourth. So this is cyanic acid, and this is acetic acid. Oh, why did I pick one with so many symbols? Good. So cyanic acid, acetic acid. Which of these is a strong acid? The answer is neither. Neither is a strong acid. Why not? Because we already defined strong as one of these. Which of these is the stronger acid? Well, we look at the Ka. The one with the greater Ka is the stronger acid, so HCN is a stronger acid than acetic acid. Now, there's also, we could ask ourselves, which of these, CH3COO minus and CN minus, which of these is the stronger base? Well, the stronger the acid, the weaker the conjugate. Now, what do I mean, the weaker the conjugate, right? We said, hey, this is a weak acid, so it is going to form hydronium plus cyanic acid. Good. So this is the strong acid. This is the acid. Here's its conjugate base. So if this is stronger than that, that would mean this is stronger than that. Got it? The stronger this conjugate, the stronger this acid is, the weaker the conjugate is. Okay? Good. So that's kind of the review on that stuff. Moving on, Kw. Okay, Kw, remember, water is self-ionizing. Good. And it has an equilibrium, meaning it has a K. And so what is that K? That Kw is equal to the concentration of hydronium times the concentration of hydroxide, right? And we know at 25C, Kw is equal to 1 times 10 to the minus 14th, right? And so if I have a neutral substance, well, what that always means is if I have a solution at 25C, hydronium times hydroxide equals that. So if they give me the hydronium, I can figure out the hydroxide. And out of all that, I can come up with the pH, which is the negative log of my hydronium concentration, and I can come up with pOH, which is the negative log of my hydroxide concentration, right? And I think we can come up with kind of this at 25, a kind of little table, right? We can say that my hydroxide concentration times hydronium concentration equals 1 times 10 to the minus 14th, and my pOH plus my pH equals 14, and these are both at 25C, right? I guess that's not a little table. That's just kind of the way it is. And we can go among these. I can go from here to here. I can go from here to here, and so forth, right? pH of a strong acid. So I have a 0.10 molar. I'm going to make it easier. 5 times 10 to the minus, no, I don't want to do that. 1 times 10 to the minus third molar HCl. Okay, how do I figure out the pH of that? Well, it's a strong acid. That means this thing does what? It dissociates completely. It's a 1-to-1 ratio between my acid and my hydroxide, excuse me, my hydronium. So that means my hydronium concentration is 1 times 10 to the minus 3 molar. That's my hydronium concentration. Got it? Good. And then how do I get the pH out of that? Well, pH is simply the negative log. And what's the negative log of 1 times 10 to the minus third? Well, it is 3. Cool. So the pH of this solution is 3. Now, you might ask yourself, what's the pOH then? Well, then pOH is equal to 14 minus 3, which is 11. Good. Now, how do I find a base? Be careful. It's about the same thing, but we have to watch out. With strong acids, I always have a 1-to-1 ratio. But if I have something like barium hydroxide, with my base, I don't have a 1-to-1. So let's say I have 1 times, well, let's make it easier, 5 times 10 to the minus 2 molar barium hydroxide solution. And we want to know what is the pOH right? What is the POH? Well, what is my concentration of hydroxide? Well, it's going to be equal to 5 times 10 to the minus 2. But how many hydroxides do I have? I have 2. So that is 10 times 10 to the minus 2, which is equal to 1 times 10 to the minus 1. And so I take the negative log of that, and what do I get? My POH is equal to 1, which means my pH is equal to 13. I hope you follow all that. Now remember, pH doesn't have to be between 0 and 7 or 0 and 14. I can have pHs that are negative, and I can have pHs that are greater than 14. Ooh, mama. Going farther. Okay, pH of a weak acid. How do we figure that out? Well, we're going to use ice. And so let's take 0.10 molar acetic acid. Oh, no, let's go cyanic acid. It's easier to write. Cyanic acid, right? And so it's going to react with that, and it's going to go to that and give me this. And I'm going to get this. And we said that the Ka is equal to cyanic acid 3.5 times 10 to the minus 3.5 times 10 to the minus 4. Good. So I'm going to use an ice box, ICE. I'm going to let this be 0.10. This is 0, this is 0, minus x, 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 0.10 minus x, excuse me, x, x. So that would mean my Ka equals x squared over 0.10 minus x. Don't want to deafen you as I cough. So we're going to assume that x is much, much smaller. So my Ka is equal to 3.5 times 10 to the minus 4th is equal to 0.1. Oops. It's equal to x squared over 0.1. So 3.5 times 10 to the negative 4th times 0.1 equals x squared. And how would I estimate that? So this would be what? 3.5 times 10 to the negative 5th, which is equal to 35 times 10 to the negative 6th. It's equal to x squared. Take the square root of both sides, yoink, yoink. That is almost 36. So I'm going to estimate this as 6 times 10 to the minus 3rd. It is my x, and x is equal to what? And then I take the negative log of that, and it's between, what, 3 and 2. And so it's going to be, what, 2.7 is my wild guess. I'm going to see if I'm right. 3.5 times 10 to the minus 4th. Times 0.1 equals square root negative log 2.2. The real answer, the real pH is 2.2. Now, I have 2 sig figs. That means I have to have 2 decimals, right? When I have 2 sig figs, and when I take the log of something, that number of sig figs determines how many decimals I have. So I have a 2.23 pH. Now, when can I use this assumption? Well, roughly when my percent ionization is less than 5%. And what is percent ionization? It is this number divided by that number. So we said our x was equal to, what exactly was my x? 3.5 times 10 to the minus 4th times 0.1 equals square root. Our x is our x was 5.9 times 10 to the minus 3rd. And I take that number, divide it by 0.1, divided by 0.1 times 100, and I get a 5.9%, 6%. I hope I did that right. 6% ionization rate. This seems too high. 5.9 times 10 to the minus 3rd divided by 0.1 times 100. 5.9%. That's good enough. It's close enough, right? Good. Any questions? We can do the same thing with a base, and we'd have to get a KB, but same kind of procedure, right? Okay, good. I love when that disappears. Ka, KB, Kw. Okay, let's talk a minute about Ka. Remember, a Ka is, let's take something like HSO4 minus, right? Now, HSO4 minus is amphiprotic, meaning it can act like an acid, or it can act like a base. Now, the reason I'm showing this is because I want you to make sure you understand what the definition of Ka and Kb is. For me to have a Ka, I must create hydronium. So my Ka here is equal to concentration of my hydronium times the concentration of sulfate over the concentration of my hydrogen sulfate. That's my Ka. For me to have a Kb, I must make hydroxide. So my Kb is equal to the concentration of hydroxide times the concentration of my sulfuric acid over the concentration of my hydrogen sulfate. That's not right. Have to change this. That's not right. We have to go with PO42 minus PO4, PO43 minus, and H2 PO4 minus. Sorry. You'll understand why that is in a sec. Good. So this would be PO43 minus, and this would be HPO42 minus, and this would be H2 PO4 minus, and this would be HPO4 2 minus. Point being, for me to have a Kb, I have to have hydroxide in that, and if I have a Ka, I have to have a hydronium. Now, that's my Ka and Kb, and then we have a relationship here among those three, and that is that my Kw is equal to the Ka of the acid times Kb, not of any Kb, but Kb of the conjugate base. So it must be the conjugate base of the acid, and that's what we can use. Got it? So let's say I'm going to do zoink. Let's say I want to know what is the pH of a 0.1 molar solution of ammonium. Well, so I'm going to do ammonium, right, plus water, and I'm going to get hydronium plus ammonia, and I would go 0.1000 minus x, 0.1 minus x, and so my Ka is equal to x squared over 0.1 minus x. The problem is there's no Ka for NH4 plus. Instead, they give me the Kb for what? They give me the Kb for ammonia, which is 1.8 times 10 to the minus fifth. 1.8 times 10 to the minus fifth is the Kb for ammonia. So I'd have to get my Ka, which is going to be equal to Kw divided by my Kb. So that's Ka of ammonium divided by blah, 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 blah. Got it? Okay. I think you can handle that. And then finally, not finally, but pH of polyprotic acids. What do we have to do with that? Well, with pH of polyprotic acids, that's something like our, let's say we have something like H2C2O4, oxalic acid. And we're going to have to run through this twice, but the point being is we're going to essentially end up making the assumption that oxalate, okay, let's draw this out real quick. H2C2O4 plus H2O yields H3O plus HC2O4 minus, and then down here we have HC2O4 minus plus water going to hydronium plus oxalate. Okay, good. And we're going to say that we start off with 0.1, fine. 0.100, we're going to do everything, and we're going to get minus x, and we're going to have a Ka1, and we're going to make our assumption, and then out of this, we'll be able to get a hydronium here, okay, based on this. And we're going to base our pH on this because we're going to assume that the amount of hydronium that comes out of the second hydrogen is insignificant. And out of this, though, we would start off with whatever we had here would come down here, and then I'd have, excuse me, not 0, whatever here would come down there, and then I'd have 0 here, and then I'd have a minus y is what we'd say, y, and we're going to get my initial concentration minus y equals, excuse me, not equals, my Ka2, excuse me, is going to be y squared over x minus y, because this is x, right? And I'm going to assume that y is much, much smaller, and x, what am I doing wrong? Excuse me. Okay, I know what I did wrong. This is not right. Sorry, folks, because this is an x here. So what I have is my Ka2 is equal to x minus y times y over x plus y. And we assume that x is much, much greater than y. So that means this ends up being xy over x. So that means y is equal to my Ka2. And what is y? The concentration of my polyatomic. So that's the way we handle polyprotic acids. I hope I didn't confuse you too much. Acid-base nature of salts. Okay, this one causes all kinds of problems. Remember, my conjugates of weak acids. So that would be, HNO2 is a weak acid, so that means my conjugate would be NO2 minus, F minus, C2O4, 2 minus. All these guys carbonate. Anything that's a conjugate of a weak acid itself is basic. And then conjugates of strong acids. So that means my strong acids are these guys, right? Well, then my conjugates, they are neutral because I have a one-way reaction here, right, ladies and gentlemen? So that means this Cl doesn't want to go back in that direction. It will not react with a hydrogen, so it won't react with water. So the conjugates of strong acids are neutral. That's true about my bases. The conjugates of strong bases are neutral. And so what are my strong bases? What are we talking about? Well, they are group 1 and 2 primarily. Group 1 and 2 cations, KOH, NaOH, and the conjugates then are Na plus and K plus. These guys are neutral because they will not remove a hydroxide from water. What else? D block. My D block cations. They will react with D block and P block with hydroxides, and they will form hydronium plus a hydroxide. So these guys, D block cations, tend to act like Lewis acids, and so when they're in salts, they are acidic. Okay? And I think I have taken care of all of that. All right, I don't want to go any longer, so if you have more questions, let me know. That will be it. Ciao.